forest that we're interested in, if we're interested in carbon, we generally have two big questions that are going to be asked for any forest ecosystem about forests and carbon with the public or with the land manager. First, there's a question of how much. How much in terms of how much carbon is there on the landscape, and a question of how much is coming in and how much is going out, right? What are our flux rates? Second, we might ask, can we affect it through forest practices? So what can we do in forest practices that affects carbon gain or loss or storage? Let's start with our current rate of carbon sequestration. Previous work in ecology has established some great theory related to how carbon changes through time in forest ecosystems. Some great theory that predicts kind of a mid-growth peak of a forest, when a forest ecosystem is middle-aged to young middle-aged, it's most productive, and then it kind of decreases in productivity through time. There's some great theory here, and there are many systems that match this. Here's a paper, though, from 2008. This figure comes from a paper in 2008 in Nature. And in this paper, they put together forest ecosystems all over the world, some tropical, some temperate, and tried to see if older forests predictably declined in productivity or in the amount of carbon that they would take up. So in this case, we're looking at net ecosystem productivity, not net plant productivity. So total carbon stores of the whole ecosystem in tons of carbon per hectare per year. It could be megagrams of carbon, it'd be the same. And you can see that if we fit a midline to this pattern, the larger graph here, you can see that we roughly might see a trend where there's an increase in a young forest and a decline to older forests. But the older forests are never really approaching zero necessarily. So they're not achieving that kind of mythical carbon balance point. They tend to be as productive. And the variation around our average is so wild that it's very likely that you have an older forest that is more productive than a younger forest, as vice versa. So there's a lot of slop around the average there. So knowing that a forest is older does not necessarily tell you that it's less productive. However, we can get some estimates here that allow us to set some bounds on our estimates for any forest ecosystem in terms of NEP. If someone shows up to you and tells you that they have a forest that is taking up 100 tons of carbon per hectare per year, you can show them this graph and say, I think you're off by a little bit. Looks like you must be off by at least a factor of 10, because in fact, when we look all over the world, this is the range of variation in net ecosystem productivity or net carbon uptake that we see. And again, this is fluxes, not storage. Now, storage is going to come into play in a minute. So remember, in carbon, we think in terms of fluxes, but we also think in terms of stores. So the way I've introduced them in lecture, we think in terms of the amount that's there, the storage, and then we can think about the fluxes. So these are fluxes. An old growth forest has far more in the bank in terms of carbon than a young forest. Here are some modeling approaches for carbon in the Kiefer forest at the Evergreen State College. In this case, we're estimating an NEP of about 3 tons per hectare per year. Currently, I think that's right around where we came out to. You can see that would be right around where the midpoint of this graph would have been. And I put some stars associated with some of our more recent estimates of live total above ground biomass, total stand carbon, and a few other estimates, including below ground carbon for our forests. The lines here represent models of amounts of carbon based on a program called FVS and their stand carbon simulator. And so it's modeled through time. And so there's an estimated predicted change in the carbon storage for the whole system. You can see that through time in our stands, we expect downwoody debris to continue to increase in our forests as a proportion of our total carbon. And in fact, that's going to be one of the big drivers through time in terms of the amount of carbon that is in our stands. We have other things like snag carbon that's going to increase through time, and we expect some predictable changes in below ground carbon, but essentially it's just a mirror of the amount of carbon above ground, which is represented in green. So that's with no management. That's if we let things just go as they're currently happening, and we might estimate where we're going to come out through time in terms of our carbon in, say, 100 years from now. But how would management affect this? Well, there are several papers that have addressed this for multiple decades. Several is an underestimate. There are hundreds of papers that have addressed this. Here's a figure from Ryan et al. In 1997. And here they're looking at stands that are a variety of ages, from about 20 years old to about 140 years old. And you can see in these stands, there's a predictable peak in net primary productivity when the stand is middle-aged, about 60 to 80 years, and declining after that. Now, based on data like these, some foresters would say, well, look, we know that following disturbance, there's known variation in NPP. And we know that NPP is going to peak when a forest is actually pretty young. So why don't we get in there and just always go in and harvest the forest once it's hit its mean productivity or its max productivity. And that way we never have to have any forests on the landscape that are in this kind of declining productivity phase. We can just always load the landscape with really productive forests. And then the landscape is sucking as much carbon as it possibly can out of the atmosphere. And isn't that a good thing? We'll take that and we'll put it in wood products. And we know wood products stick around forever. So then everything's fine, right? Okay, that was a little loaded monologue I just gave you and probably not representing reality. So let's dive in to a paper that kind of dug into this a while ago. So here we're looking at a paper. This is maybe 30 years old now. And this debate is still going on because there are some hard concepts to grasp here. So in this paper, the authors wanted to look at the effects on carbon storage when you convert old growth forests to young forests. So if old growth forests really become less productive with time, can we convert them to young forests and have a whole landscape full of young, productive, thriving forests? What is the effect on carbon? Well, let's start with some assumptions. First, there's some clearing activity that takes place. It opens up the stand, it changes the environment. Now, this could happen naturally due to wildfire, or it could happen during a harvest. But depending on whether it's fire or harvest, you're going to have some different conditions contributing to carbon change through time. In a wildfire, you have a large amount of, you have a lot of large material that's actually left over sitting on the landscape. So you haven't quite lost as much material. You have many large bowls and large charred snags on the landscape. You lost a lot of fine branches and small litter, so you did lose some carbon, but you also increased the char in the soil, and that's not going to decompose very fast. Compare it with a harvested forest. You've opened up the stand, there's more light, there's more moisture, there's more heat, and you left a lot of fine material around on the soil that's going to decompose pretty rapidly. And then you pulled away the large material. Now you pulled away the large material and you sent it off to a sawmill. When you do that, you're going to saw up part of it. So you're going to end up with a tremendous amount of sawdust. That sawdust is either going to be burned to power the sawmill, which is how people used to do it, especially in steam-powered sawmills, which used to be the rage and they're not necessarily around anymore. It might be burned for biomass, or let's say even it's converted into chipboard. Regardless, it's converted into some material that has a lifespan. Now, if you think that creating chipboard or creating a piece of paper means you're creating something that lasts for 500 years, the age of an average old growth tree, you're really fooling yourself. They don't stick around that. Things don't stick around that long. I guess there are ways that we could take logs off landscapes and bury them in the water and ensure that they don't decompose, but generally that doesn't happen. And so we have to have some assumptions about that material. When you take all of that into account, when you log a forest, you're not losing all the carbon. So the graph here is showing percentage of old growth storage. You can see we're starting at 100% and we're dropping down. In a wildfire, maybe we're dropping down to 60% of the carbon that old growth forest had before it started. in a harvest, we're generally going to drop down around 40% of the carbon that landscape had. And that's after accounting for all the different places that carbon can go. Regardless, we're going to lose a large amount of the carbon in that system. And that's just undeniable. There are portions of the tops of trees, branches, other things that are going to decompose rapidly, sawdust that's lost to mills, and the constant decomposition of products that we produce that are going to result in some loss of carbon to the atmosphere. It's just undeniable. And through time, we would expect first, we're going to get a major decline in the carbon just in the stand itself as that fine material, the little branches and needles, continue to decompose. So they're lost to the atmosphere through decomposition, and the total stand carbon is going to decline. Through time, though, you're going to build up material, young, vigorous, fast-growing trees, and look at the slope of the line as it increases. It's going to increase again rapidly. And so as this forest reaches a middle age, we're going to come back to approximating the amount of carbon that was present when it was an old growth forest relatively quickly, because those forests are growing fast. But what are they growing to? They're just growing back to the same amount of carbon that was there before we messed with it. So even though they're growing fast, the amount of storage that they're ultimately going to achieve is probably going to be about the same. So this is equivalent to giving up all your money in the bank so that you can earn a higher paycheck. You can do that, but there's an amount of time you'll need to wait before you can earn back the same amount of money in the bank. Okay, sorry, long monologue. What happens when we harvest a forest? So when we harvest a forest, we're going back in and we're interrupting that return to those old growth carbon storage conditions. And so the seesaw pattern in this graph here is showing that a stand through time that's repeatedly harvested, say on a 60-year cycle, is going to continually increase towards the former 100% of old growth storage, and then get cut again, and we're going to lose it again. Then it'll increase, then it'll get cut. It'll increase and it'll get cut. And so note here that by harvesting, we're not removing all the carbon from the system. There's no way that's happening. There are some different assumptions in these different curves. The dotted line curve at the top assumes that residues are left and 50 and 45% of the wood is put into long-term storage. And so if we do that, we can increase our progression and our carbon storage so that we're getting closer to the old growth storage. Note that we're not getting all the way back up to the amount of carbon that was stored in the old growth forest. We're just doing better than we would if we burned our site and didn't store our wood well or converted it into easily decomposable products. Let's get to a take home. Conversion of old growth forests in the Pacific Northwest has been a significant source of carbon in the atmosphere. In this paper, Harmon et al. Went through and tried to calculate for the Northwest how much old growth was lost, how much carbon did that result in, and let's put an actual number on it. Through the conversion of old growth forest to young forest, they estimate 1.5 to 1.8 billion tons of carbon has been added to the atmosphere in the last century. That's billion, 10 to the 9. Here's an example from a forest like ours. This comes from a master's thesis at the University of Washington. In this graph, you can see tons of carbon per hectare in an undisturbed forest, the green line, and a variety of different rotations of forests. The small dips that you see, for example, in the red line there, represent coming in and doing intermediate thins before large cuts. And so you do some pre-commercial thins, maybe a series of 2 pre-commercial thins before you do a large cut in that forest on a 120-year rotation. In the orange line, the 80-year rotation, you do 1 pre-commercial thin. So pre-commercial thin, you're just coming in and cutting the trees that are smaller and opening up growing space for the remaining trees. So you're reducing competition and making your remaining trees grow faster. So this is in general the same conclusion that we would come to when looking at Harmon et al.'s work. So you'll notice that regardless, we're not going to come out on top here unless we do nothing. And so really the silver bullet here in forest management of late has been thinking, okay, if the green line is do nothing, and that's maximum carbon storage over the long term in a forest ecosystem, regardless of the instantaneous rate, are there ways to manipulate the forest or interact with the forest such that we actually get higher amounts of carbon than the green line suggests? So this is a question that forest managers get frequently. Is there a way that I can cut carbon on my landscape and remove it to the mill and somehow be left over with more carbon on the landscape later? And that's a hard puzzle, but thinking wisely about or being smart about individual species and their natural history on the landscape, there's potential to be able to interface with forest ecology in a way that we might be able to do that. So some species decompose faster than others, for example. So stocking the landscape with species that don't decompose as readily possibly could lead you to higher carbon storage over time. If you can regulate, if you can down-regulate the amount of carbon that leaves the system, even if the amount of carbon coming in is slower, you can end up with higher carbon storage at the end of the day. And this brings us to all of these questions about fire. Now we know that photosynthesis is fixing carbon. We know this normal situation where plant and soil respiration are occurring, and we have these curves in carbon through time. But then we have these large natural disasters that we're dealing with. And our modern fire situation probably presents us with a whole different set of variables to think about in terms of carbon storage on the landscape. Our landscapes are being changed by large disturbances. What does that mean for carbon on the landscape? How does the remaining material decompose? And what about all of the smoke and aerosols and things like that that we see coming off of these forest fires? Where does that go? What does that mean for carbon storage? That's it for this talk. It's been a big talk. In the next videos, I'm going to go through and I want to do a deep dive into some spreadsheets where we'll look at how to actually calculate and add your data to a spreadsheet to calculate carbon for your forest. Regardless, though, I hope you're walking away with this realizing that from a simple set of measurements, hands-on measurements in the field, you can calculate the amount of carbon, and it's better to start doing this earlier rather than later. The more data we have from the past, the more we're able to say about what's going to happen in the future, and the past starts now. Well, it just started, but it started. That's enough for now.